Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and here's another video on the larger Dualpole kit here. And so what the difference is now, what we have is much bigger rotors. I showed this before, but not running. So what we have is just over an inch thick rotor. Originally we had 3/4 inch, and then we went down to 1/4 inch to save some money, and now we have not only a thicker rotor, but before we were using 1/4 inch thick magnets by 1 1/4 inch wide. Now we're using 1 1/4 inch wide by 1 inch deep magnets. So there's a lot more magnets to this motor now. So a lot more torque. So again, we're like the mini kit that we did upgrade recently to the thicker rotors. We want to do the same here. And in doing that, we have an attraction and repulsion motor. So we're not talking about a traction mode in which we are spending energy to attract the magnet into the pole piece on the coils, but we are talking about using the natural attraction. You can see how strong the magnetic lock is, but then it kind of spins once you get it going. But once we pass top dead center, then of course we pulse it. So there's a lot more torque to this motor now that we've done that. So we still may change the coils to another configuration. It's just a little bit too much power right now. We got to do the settings on it. So here's another model here with different coils, and we will probably upgrade to that. But these are, I wanted to show this system with the coils we've been selling for years. So again, 8 strands of 18 gauge wire, and filling up the 3-inch spool. And so each one of those is going to a MOSFET here. And of course we still have the same circuit, the gate driver. In fact, we've got 2 gate drivers on here, one for 2 MOSFETs. So then we have all the same things that we talked about in the last video, where we have to deal with the voltage spike across the MOSFETs. So here, again, 12, 24, 36, 48 volts are going to have different capacitors across the MOSFETs. And we want to consider that these are 500 volt MOSFETs, so we want to keep well with under that 500 volt limit. Otherwise the diodes not only produce a lot of heat, but they get ruined in a real hurry. Once they're ruined, they still will work. The MOSFET will still work, but it's damaged. It's going to produce a lot more heat, and that's very important to understand. So again, the voltage changes. We're talking about the spike voltage, not the input voltage. Input is only 12 volts, and the spike, even though there's a charging battery, there's still a significant spike across the MOSFET. So the MOSFET spike will be determined by the amount of inductance in the motor coils, as well as the input voltage, and then of course the amperage. So we're going to run this today just with and without the generator coils connected and loaded, and we're not going to load down the rotor or the shaft in addition to that, so we can be fine with these caps at those levels. And we'll look at the oscilloscope to determine that. So I think we'll get up to over 160 volts, I believe, on there, so that's fine. And this is kind of the setting that I would use for the 1224 volt. Like I said, if you're only running it in 12 volts and we're only running it with the generator coils loaded, then, and here we have a battery being loaded as the load or an LED again. So if we are only going to run this lightly at 12 volts, then we could actually reduce the size of these capacitors. And we can bring that voltage up, so therefore we get more charging in the charging battery. So again, the charging rate is proportional to the spike that you see even across the MOSFET. And the more capacitance you add, the more of a snubber system exists there. So in this case we have the regular diodes here, which are slow. They're not the Schottky diodes. There's a reason for that. One being it's convenient to mount this this way for this setup, and two, there's a lot of power flowing through here and it's tricky. We have to decide on the right kind of diodes there to use. The Schottky work really good, but these work fine too. So anyway, that's pretty much it. It's all the same. Oh, the other thing is what we're doing now with this, because the magnets are so strong, the fields are very pronounced here. The timing is very sensitive. On both the small motor and the big motor is true. So what happens is we're using two Hall sensors here. So we're going to start it with the timing way after top dead center, like about 1.5 inches, a little bit more than 1.5 inches after top dead center. That's where it wants to start. So it's almost right between the two magnets. And then once we get some RPM on there, we switch over to just after top dead center. And of course I've got some wires here that are holding this together. 12 gauge wire, that's what we're using for the generator coils, which are all in series with each other. So what happens is, in the code, we'll be doing that later this week. So what happens is, initially, it's going to get it started with Hall number 1, which is on pin number 3. I think that's what we'll do. Actually, probably pin number 7. And then pin number 3 will be continuing to use, actually pin number 2, sorry, will continue to use to run it normally once it's up to speed. But here I'm just going to show that with the switch, just a toggle switch to change between them. So then, like I said, we got 12 gauge wire for the generator coils. They're going to go into this variac, and we're going to see the square wave. It's a pretty good square wave coming off of that, going into the bridge. I've got a big bridge there, and then we have another battery, equal battery. So that's probably one of the best ways to run the system, where you're charging a battery bank, and then you could run an inverter off of it directly. You could get into pulsing the battery, whatever, but there is a pulse already. You'll see a square wave across the input of the bridge there. So in this case, the generator coils shorted are not speeding up the motor because the magnets are so powerful that the generator action is overwhelming it. So we'll look at that with the variac in a minute. When we turn it all the way to the highest voltage on the variac, again we're going backwards with this. We're going into the output, and then we're coming out with the input with the variac here, so it's backwards. So when we turn this all the way up to the highest voltage, then it's open in the sense that it's not loading the motor down. So you'll see the amperage change once we start loading it, and then so forth. So I suppose we could look at the RPM and all that as well, but so anyway, this can be used right now. Maximum is about 80 amps, so we're going to run it at about 14 amps, and it's going to start up around 60 amps initially, and then get up to speed, and then even when we're loading it with the battery, it's going to be only running about 14 amps at 12 volts. Once we go up to 24 volts, then the amperage is more pronounced. It's a much more powerful motor. But again, you can load this thing down. You know, you're going to slow down the RPMs, but it will. You can load it down significantly. Like I said, the maximum is about 80 amps. That's limited by the coils and the heat produced in the coils. So again, the input is equal to the output. These batteries shouldn't be run more than what we're doing today because they off-gas and they only are 35 amp hour batteries. So if I was going to do, maybe in the second half of this video we'll bring it over to the shop and run the golf cart batteries, and then you can see it running at 24 volts with higher amperage. I mean, we could still use 24 volts on these smaller batteries, but if we're going to go to that trouble, I think we need to do the golf cart and run some bigger loads on it. Golf cart batteries, I should say. So, I just want to make sure this is all lined up here, and we should get going here. So I'm going to run the oscilloscope across the charging battery. I think you can see it's sitting at 11.92. I was running it for a couple of minutes. So what we're going to do is get this thing started here. Let's look at the ammeter. going to be upside down, of course. Actually, it's right side up. Alright, so it's going to make this ding sound a little bit. Ding. It's energizing the coils. Alright, so we've turned it on to hall number 1 right here. And then we're going to flip over. So we can look at battery voltages if we want to. So this one's sitting pretty charged. I was running it for a little bit, so it discharged a bit. 1306. 1210. Alright, so 1192 is on that battery. And so we'll get this self-starting this week as well. We just have to have the input pulse set higher than I have it right now. But anyway, it doesn't take much just to turn it slightly. So you can see the amperage is about 20 amps. 30 amps, so 40 amps right there, and then it's going to come down. Of course, once the amperage is high, you can see that charging battery is getting a lot of power to it, so it's really bottlenecked. It's a very small battery with that many amps, and it's not really all amps either, but it's, I'm talking about power. So we're going to look at, first of all, we'll look at the charging of the battery. So now I've turned it on. It's at 14.5 amps input. And we've got a nice square wave on this. So you can see 26 volts peak to peak. And so now if I turn this up, we can see the amperage on the input battery is not changing at all. It's actually going down a little bit now. But now I'm driving that battery pretty hard. So 27 volts peak to peak, 12.10 volts on that battery. Not sure if this can be seen properly, so I'll move this around. 14 volts. And what we have is a bridge rectifier. So you can see the battery there. So I just have the variac output coming to here, coming around to this bridge, and then I just have the scope across the AC side. So you can see a nice square wave. Adding capacitance to it is another matter. So you can see the square wave is no longer square when I add the capacitance to it. It does not increase the charging rate. It actually decreases it. Because why? We talked about this before. the pulse needs to be as sharp as possible for maximum gain. So the more abrupt, the faster the rate of change, as Tesla talked about, the better. So we're charging pretty good, this charging battery. We'll look at the input battery right now, see, it should be down. Of course, there's a voltage drop, 12.4. It's reasonable. So there's also a speed control here. We can adjust the power rate. So now we're at 12 amps, 11 amps, 10 amps. You hear it slowing down. See, this battery is going to charge less. So now there is some things to understand about that. Because the magnetic fields are they're so close, the magnets are so close to each other, actually it's more optimum to run this, to turn down this, the on time, which is what this pot is doing, intensimeters. And at the higher voltages we have to limit this more. So we're at like 8 amps right now. Now I'm going to turn it back up. 14.5 again. So it's climbing back up to speed. Look at the temperature here. We're running at basically room temperature. It's a few degrees above the ambient. It's got water cooling in the assembled kit. So therefore it's maybe bring this up a little bit. How's that? Okay, good. Alright, so we don't need the water cooling because we're not loading it down hard enough. It's not creating heat. So that's a lot of power going into that charging battery right now. Again, if it was different load, it could load it down a little bit more. So we can turn it off. And the amperage goes down, of course, 12 amps. And you can see the battery is coming back down. It's not a high frequency, well, I guess it is. 337 cycles per second. Hertz. Turn it back on there. So now, of course, you're supposed to turn the variac only when it's turned off. The voltage on the variac shows over 150 volts. I did that. So now what we can do is change the load again to the SCR or the LED. So you can look at this voltage. We ran for a couple of minutes there. The battery is charged somewhat. So now what we're going to do is turn this light on, and of course this is a 100-watt module, so we have way more than 100 watts going on here. So I can't push it too hard. Otherwise it will blow the LED out. So that's over 100 watts there. It gets really hot fast, so we only run it a little bit. It's very bright. So those are the two loads that we can do on the motor. And I think what I'll do is I'll go back to the battery right now. And then what we'll do is load it down a little bit. Try and load the shaft down here. Like we did the little one, except I won't be able to. Okay, so you can see the battery is coming back down in volts there. So what we're going to do is run it again. Oops. And then I'm going to attempt to instead of holding the shaft, which is not going to do any good because I won't be able to load it down very much. Holding the side gives me more torque. So we can bring down that RPM. So of course it charges up really good. Too much for these batteries. Almost 16 volts there. It's about 100 hertz right now. So it's quite a bit of torque there beyond what we're already using on the generator coils. I wouldn't be able to hold this shaft down. It's not going to give me. But we're still at 27 amps right now, 28 amps. So anyway, what we can do is run other loads, but we probably want to do that at 24 volts. So again, we can go up to about 80 amps. 12 volts, you're not going to get that as much, as easy. So again, we got 35 volts there. Now what we'll do is turn it off. Oh, I know what I was going to do. We have to look at, I shouldn't have turned it off, but now we've got to wait till it stops. You want to look at the oscilloscope across the MOSFETs. And you'll see I'll have to probably do the 10 times probe on that. So we'll get it started again now, and we'll look at the oscilloscope while it starts up. You can see now all the voltages. This battery is going to come down, but it was really being charged too hard. So again, the timing's already set, so all we have to do is connect up. If you're going to disconnect these wires, wait till it stops before you connect it again. because that initial pulse will not be good for it while it's running fast. That's what I did in the last video, and that's why I blew out the MOSFET. Alright, so what we're going to do is get this started. We're going to look at the scope. This is going to reset so that so we have so you can see the waveform now. Anyway, we're at 43 volts peak to peak, 47. So what we want to look at is a couple of things here. So what I'm going to do is put the camera closer. So what we have here is so you can see it. So this is the on time here, or this is the on time, this is the off time, and you can see the pulsing. Or the ringing. So there's the collapsing of the coil, the second pulse, right? You have to, that's where people think the only energy is charging the battery. Generally they think of the collapsing of the coil. So this is the second one. The first one is on the other end. Oops. First one's right here. When we turn on the MOSFET, so there's a little bit of a ringing there. And again, the abruptness of the switching is important. The sharpness of the pulse is really important. So when we look here, see, we can see the dip. So this is because of the capacitance. The capacitor charges up and discharges. So we can look at this in determining which capacitor we're using. Right now the capacitors are way too big for what we're doing. But we'll load it down a little bit and take a look, see what happens. Need to look at it while we're doing this. So as I load it down, so you're going to see this change somewhat. As we draw more amps, the waveform changes. The peak to peak goes up as we draw more amperage. So now we're at above what we can see.
So we're at 60 plus 26 amps, and we're still not very high, but we could see the ringing changing quite a bit here. Now it's getting too hot to hold this thing. So MOSFETs are still pretty cool, even though we're lowering them down, even though MOSFETs can handle 2,500 watts each. So again, you can look at the waveform there, see what I'm talking about. So this is 2.2 microfarads at 600 volts. And so as we climb up here, we're back to the 14 amps. You can see the waveform change. Now, if I disconnect the load altogether, we can look at that. So watch what happens now. Not much difference. The amperage has changed a little bit. Disconnect it. So that's what I'm talking about. So I turned off the charging of this battery right here, unplugged it back there, and you can see it's coming back down voltage. So we'll turn this off. So you can see the waveform, which is interesting, as we turn it off. What's happening across the cap. So it's 28 volts peak to peak still. So that's 28 volts above 0. It's coming down. Still 25. So there is a lot of activity going on here because of the very powerful magnets. It's a different type of motor now. It's no longer just a propulsion motor. So now we're 16 volts only. So in other words, we still have activity across MOSFET, even though it's not switching. The power is getting shuffled around. So this gets back to the Tesla shuttle circuit idea again, where we're shuffling around the energy. Now, of course, we're doing this primarily
to the shaft is burning hot because I was loading it down with the cloth. But anyway, what I was getting at is, of course, we don't need this ammeter now. Is we're shuffling around the energy. So the cap was primarily intended to protect the MOSFET, even though it has capacitance across the source and the drain, the two main terminals of the MOSFET. What we're doing is, you can see on the waveform the charging and the discharging of the cap, and so it sends it back in to into the motor, and also it charges the battery. So what I didn't show here, I think I showed in another video. Well, I can't really because of the connections. I have the primary positive wire going directly to the charging negative terminal, just for convenience. So normally there would be a Y connect. Well, there is a Y connection here because I have it then going over to the primary positive. So if you check the amperage across this wire right here, and then you were to check the amperage across here, you'll find a difference. So what's happening is that the charging battery is also contributing to the motor input. And that's pretty interesting, because if you're going to check amperage right here like I was doing, it's different than right here. So the amperage coming from the input battery, while it was only 14 and a half amps, if you look over here, it would have been something probably like 18 or more, depending on how hard we push it in the various settings. So, you know, that's interesting to observe and understand how this whole thing works now. Again, the amperage is not, like the amperage across these output charging positive lines here coming from the end of the bridge, the positive terminal of the bridge, is going to be very low. But the battery is nevertheless charging because it's not amperage that's charging this battery. Some of it is because the cap is dumping and it's going back into this charging battery. And so you can measure that amperage and see that to some extent. And again, it's in peak pulses and all that, so there's all sorts of activity going on. Nevertheless, the battery charges up in a way that's very unusual, and it's more involved now than what we used to do because of the capacitor here. So, you know, it does charge at the rate that this discharges. It still has the negative pulse. You know, we're sitting at 1284, 85, and it will come down some, and we can look at the input voltage. So we definitely discharged this battery pretty hard. We were up, so we're at 1270 though. Sounds like a fully charged battery. 1270 is considered fully charged. The conventional system. So that will come back up. That's why I talk a little bit while the voltmeters are still displaying the voltage. This battery voltage 1207 is coming back down. It was 1290 or 1192, and that was still coming down a little bit because I had run it before the video started, just a little bit. So the charging rate of that battery isn't at the same rate of this battery, but we're hardly using any torque to do that. Once we load down this shaft, ouch, still hot, then what happens is we'll get, we can use the torque on the motor itself in addition to the charging through the variac. And we don't need the variac, we can go straight out here to the bridge, but the variac gives us that change of power that's nice to have if you're wanting to run different loads. Like, I certainly can't hook the LED up directly because it's, hundreds of watts. Well, I would say at least 200 watts. I mean, we were only running this at 14 amps at 12 volts. That's actually very little. But we would easily go over the 100 watts. And that bulb would, well, I have, as you know, I blow up parts from time to time. So, yeah, so we would need at least 2 bulbs. Maybe, yeah, at least 2 bulbs. So yeah, 140 or 14 amps, 14 and a half amps at 12 volts is going to be, we could run probably 200 watt LED modules with that and get very bright. So again, this motor really isn't meant for 12 volts. It can do it. Like I said, you can load it down, but because of the windings of the coils and all that, we really essentially made this for higher voltage. In fact, I originally made these way back, the first models, the monopole models, we made for running over 100 volts. Nobody seemed to want to do that. But nowadays, people run solar systems around 48 volts, and that would be typically what you'd run this one. Then you could get up to about 4 kilowatts with this when you're running an external load in addition to the generator coils. So again, open or unloaded shaft, the generator coils are going to put out just a little under the input, and you can run different kinds of loads like we showed before. You can run resistive loads, but really capacitive loads are the best, most responsive, because we're using that, you can see that sharp square wave boom, which is good for amplification. So it's creating, according to the rate of change in the pulse, you'll have more output amplification in that pulse. So using a capacitive type of load will appreciate it more. So a battery works great in that regard, and you could do other kinds of loads as well. So A battery with an inverter, the inverter will have capacitors across it, so it will absorb those pulses more, it will smooth them out. But it'll still provide decent power. But ideally, you pulse the battery, then you run the load. It's not really convenient to have too many batteries. And again, people always want to run the input, and it's never efficient to do that. And it's hard for people to understand that. They're like, why? So ideally, you have separate systems. An isolated system, which this is an isolated system, works better than a direct connect. You can't really directly connect. You couldn't run the, well, we are using the output to run the input, as I mentioned earlier. So you couldn't completely loop it around with this configuration. Again, going back to these capacitors, so these capacitors, these 2.2 microfarad are overkill for what we're doing here. So they would be more suitable for running at 24 volts under load, you know, especially if we get up towards the 80 amps. Like here we were only doing maximum about 40 amps at startup. And the generator or the motor coils are not even getting warm, they're still room temperature. But towards 80 amps, I mean, they could go 25 amps maybe at the most. That's what I've usually definitely limited them to. But the problem is the center of the coils are hotter than the outside. And once they get hot in the center, they'll hold that heat for hours. Even when it's turned off. So, you know, so that would be, you know, a 100 amp system if you really watch the heat, you know, put a thermal switch on there, then maybe having some airflow. Now there is some airflow coming through because we have some channels here, some open holes inside on these plates, so it sucks the air in, which is like the Tesla turbine concept. So it does circulate some airflow the faster it spins, but generally when you're loading it down, you're not spinning it as fast. So again, if we want to look at these caps, and we were to do what we call the third stage process, which is across this line here, putting additional inductors. Again, that adds more inductance to the system at a different phase. So what happens is you will have this, even though you have a load across that inductor or transformer, there will be a pulse back into the input, and therefore you have to have suitable capacitance across the MOSFET again, because it will at least double the voltage, depending on the inductor you're using, of course. I mean, if you had too small an inductor, then you'll blow it out. Like in the video, last video I showed, evidently either the clip wasn't conducting or the LED output was blown out. So I exceeded the voltage of the MOSFET, and therefore I damaged the internal diode when I ran it too long. And then I attempted to turn it off, but then while it was still running, I plugged it back in. And then it blew it out. But anyway, that's not the point. The point is, you have to watch that and balance that out, because the spike is going to be higher. And again, you could have a capacitance across the input, and that changes things. It adds more, you know, voltage, depending on the inductor you're using, of course. I mean, if you had too small an inductor, then you'll blow it out. Like in the video, last video I showed, evidently either the clip wasn't conducting or the LED output was blown out. So I exceeded the voltage of the MOSFET, and therefore I damaged the internal diode when I ran it too long. And then I attempted to turn it off, but then while it was still running, I plugged it back in. And then it blew it out. But anyway, that's not the point. The point is, you have to watch that and balance that out, because the spike is going to be higher. And again, you could have a capacitance across the input, and that changes things. It adds more, amperage. Usually there's, wires from these terminals here going to the battery in a distance, and then we put a capacitor right across those 2 points there, 2 terminals. But we don't need that really, or very small capacitance there if we are going to do that, because we already have this capacitance. So you have to think in terms of the fact that even though the capacitor doesn't have to be exactly parallel in order to influence the circuit, especially with radio frequency. You have one end of the capacitor attached, it will still influence the rest of the circuit. I mean, mind you, with the low frequency, it's not going to, if you just had the capacitor, only one side of the capacitor connected to anything, then it wouldn't really do anything. I'm not talking about that. But with radio frequencies, that is completely different. Even with one end of the capacitor plate connected, you will change the capacitance of a resonant circuit. So here we can work with resonance as well across this output line, and then we could multiply loads here indefinitely. If we have the right core material or air core in resonance with the motor, so we lock down the RPM, which we have a code for that, and like a governor system that keeps the RPM the same, and then we use that frequency with a resonant circuit here. Then we'll produce a lot more output, and you don't want too high output because it will again come back into the input. So again, it's a balancing act. Start with high capacitor values, and when you're experimenting, because that's why, again, I didn't show this a couple of years ago, because I knew what was going to happen. And now I know the sale of semiconductors is going to skyrocket because people are going to be blowing them out in doing this. Now that I've shared that, it's funny because when I do mention certain part numbers, parts get sold out and I can't buy them anymore, like what happened with my one set of FETs that I bought. They're no longer available for a year. So anyway, let's look at the voltages again. We're looking at 1203, it definitely did charge the battery. 1204, by this time these voltages have stabilized somewhat. 1279 has gone up significantly in this battery. This charging battery, 1273, 72, 73. This battery has come down from its 13 volt, 1306 or something. But again, these are Renaissance charged batteries, so they operate at a higher voltage, higher resting fully charged voltage, and they also can go really deep discharge. So what happens is, as I said in the one video which I deleted, the solar video, I'm going to do another video for those who are asking, and that's another story. So anyway, what I talked about in that video was the fact that our batteries with this charging technology can, you can get more capacity at the lower end, below 10.5 volts. So I'm not afraid to deep discharge them. We can go down to 0 you know, it doesn't matter to me, I do that sometimes. So the point is that we have real capacity at all throughout the curve of the battery from 13.3 volts. These batteries will charge and rest at 13.3 volts. Or actually maybe 13.4. And that's not because they're sulfated. They're not sulfated. And this one, again, was in my Porsche, which was, we had this battery since 2010. Probably around there. I guess there's a date stamp on there somewhere. So, you know, the batteries still work great, even though they're AGM batteries. I don't really want that. But these were kind of showcase batteries, so we use them. It's just what they are. So anyway, I think that's it. The things left to do this week we're going to do on this is change the code so that it self-starts and it has the two halls that it switches between. See, the thing is, as we go up in voltage, we have to adjust this timing, and we have to have a different code above the 24 volts. Anyway, so these will be models. Oh, what I'm going to do from now on, this is another thing to mention. So the chip, the Arduino that we're using for the speed control now has a chip on it which can, so what we'll do is we'll provide multiple chips with each order that you'll run 1224 and then 3648, as well as provide the different capacitor values. We'll put the one in there that, assuming nobody's going to run a load on the shaft, and then just use the generator coils, which are optional in the bigger motor here. So you have to order those separately. But assuming that you're going to run it lightly, we'll provide the cap in the circuit already connected. Well, this one isn't assembled unless you order it assembled. This part is, but not this part. But anyway, we'll put in those parts with the order on the big one and the small one, and then you can pick and choose which ones you use. And this video will be the basis for explaining that. And then, like I said, if you don't have an oscilloscope, you can just put in the ones that we give you, and you can always be safer by putting the bigger ones in. But again, charging rate will be affected by the level of capacitance you use. So I think we don't need the oscilloscope on anymore. So again, we're at resting 1202, 1203. So that's gone up 1/10 of a volt for the little bit of time we were running it. This battery, 1277, is pretty much where it's at, where it's going to stay. And this one, 1273, that will come back a little bit more over time. Hi, I'm going to do one more test here before I go up to 24 volts. So what I have is a bulb here, and we're going to look at it. So resistive load, incandescent bulb. So let's get this started again. Oh yeah, and then I do have a new code, but I didn't install it yet. That I don't need to pull the switch. But anyway. It will do that automatically. Whoop.
Need to get it going a little bit faster.
There we go. Probably move the timing a bit there. Anyway, we have the incandescent bulb here. Of course, they're not very efficient. So we will put the lights here and see. Not nearly as bright as the regular bulb or the LED. Anyway, it's heat lamp. So what we can do is look at the voltage on it. So again, this is just at 12 volts. It's only running at about 150 amps here, or 150 watts. So what we have is about 113 volts AC, but the difference is, if you look at that close up, well, might as well just bring the camera over. Alright, so we have 114 volts, that's your, but the sine wave is a pure sine wave, of course, true sine wave. And so we can expand it. So a little bit on the top and the bottom that isn't quite pure, but we're not at 60 hertz. We're at 205, 210, 211, 15. So what we have is a faster frequency. So there's more power. That's why we get more of the LED in the capacitor, because we have a higher frequency. So that's why it's much lower with these bulbs. So I'm getting about half the power from the input. I mean, it's not coming at all from the input, but that's the charging battery there. And we can see here the amperage. You know, about 15 amps. And then if we move the voltmeter over, and we'll see the input is only 1163 under load. So if I disconnect the bulb, we'll look at, alright, so I'm disconnecting it. So you can see the waveform is going up. Now we're at 400 volts peak to peak, and the frequency is obviously going higher with the RPM. So it's going to keep speeding up. There acts under not full power. Like when we turn it up,
so let's go back to where we were. See, the amperage came down when we did that. In this case, there's a lot of generator action in this motor, more than the little kit. So now we're back, well, we're getting closer to that low spot, and we can turn the variac right now higher. And so our voltage is different here, but then our amperage, anyway, when we do, this is the right bulb for this particular setting. This voltage right now is correct, but again, it's for a 60 hertz bulb. So anyway, if we go to a bigger bulb or a smaller bulb, then it's out of balance, and then we would have to adjust the variac and so forth. But anyway, so this is running in the lightest mode right now. This is almost like the little mini kit. So this is not what we made this motor for. So we'll go up to 24 volts next, and we'll run some much bigger loads at 50 amps or so. But I just wanted to show this because it's easy to see this kind of load. Again, if we're trying to do a resistive load, this is the best way to show it here. But again, charging the battery and a capacitive load is much better. Then you can get more, like if I have two of these 100 watt modules, I'll be able to light them up to pretty much full brightness, two of them, but I can only run that bulb, which is representing about half the power. Well, it's a little bit more than half the input power, so that's not as good. But of course, you have the higher frequency. So what we can do is actually run bulbs in series, like I mentioned before on the other video on the smaller kit. So anyway, we're charged up the other battery. This one's come down, and we can again turn it off. So let's look at the waveform as the bulb gets dimmer. You can see the voltage going down. There's no hidden wires under the table. Well, anyway, let's look at the waveform first. And then, so now we're at the 60 hertz there, close right now. Just before it stops. And then it's hot. So you can see there's no hidden wires there. Alright, we're back for more here. So we're set up at 24 volts, and we've updated the code to do the two Hall switches here. And so a couple of things to notice. The timing changes according to the RPM. That's why we have the two Halls on here. And so if we're going to run a heavy load like this, then we have to move the regular Hall, the one that normally is the signal for the motor. This is the startup one here, which is quite a bit after top dead center. In this case, this second Hall is pretty close to it. About a 3/4 of an inch after top dead center, and this is a little over a quarter, or over 1 inch, and so that's where it likes to be.
with these particular coils, we can't do the startup, self-starting, I should say. With the other coils in the other setup I was just showing, which is probably what we're going to go with from this point on. I just need to do a little bit more work on that. We can do the self-startup. So if you order this, that's what you would be getting anyway, because we're not going to be doing these coils anymore. These are the older coils. We'll just have one wire coming out instead of 8 strands per coil. But anyway, so we have to retard the timing with the lower RPM. So as it gets up to higher RPM, we can move to top dead center. So the other thing to notice is the generator coils we're putting over 1,000 volts, like 1,400 volts, this 24 volt input, very high RPM, and so this is not really for resistive loads, like I mentioned. You'll see right now we have the settings turned down quite a bit, and we have the LED, and as soon as we pulse it, you'll see how bright the LED flashes, and I probably will be damaging this LED. I guess I'll turn it down a little bit from what I just had it on. It's pretty bright. So we're going to be doing 50 amp average, approximately 50 to 60 amps here. Now this is not good for these batteries, so we're not going to run it that long. But this is a very big industrial fan. I show this at my conventions usually, and so now this will be the first time I'm actually showing this running, I believe. Initially we used to put this in the original case, and I used to drive it around my conventions and put it on my roof of my car or my trailer, and but then I thought it's easier to attach to the shaft. But we did hook it up with a pulley system before on the older model with the thinner rotors. So this will be really putting out quite a bit more than horsepower. So it'll be like 1.5 horsepower or something like that. So we've got, let's do the calculations here before we get started, just to let you know. So if we have, say, 50 amps at about 24 volts, it's 1,200 watts. Now the thing about it is, it's not really the right calculation, because the way this is working, it's not really draining the battery as fast as that. And you can see now that I've separated the wires here, this is the input wire, positive, and this time I have the clip on the input positive terminal. So we'll see that there'll be a 2+ amp discrepancy between this wire and this wire. So in other words, the charging battery is adding amperage into the system. I mean, however you want to look at it, this whole thing doesn't make sense at all according to the regular amp meters. They can't detect how the rate of charge, because we are charging these batteries. The left or your right side voltmeter here is this battery, the charging battery bank here, and then the bigger one is for the input. So the batteries charge at the rate that the other one discharges, and yet we see no real amperage coming into these batteries at all. They can't really detect that. So yeah, so anyway, this is really blowing around all the papers in the room, and it's going to want to take off. Now this is pretty heavy motor. This is with the generator coils, the big ones I have here. This is about 70 pounds of weight on this, so it's not moving anywhere. But it will blow the air here pretty good. So let's we'll look at the scope again across the caps. 24 volts. It's only I just took a picture of it. What was it? We're going to see the scope shot here. So what I have here is about 120 volts peak to peak. Now that was without this fan, so it should go up a little bit. Like I said, under load there's going to be a higher pulse. Like you see, as soon as the first pulse hits, the output of the generator coil is going to light up. Boom. This is where the generator coils are receiving a lot more power from the motor coils, from their EMP, electromagnetic pulse. Boom. The harder the pulse, which is under amperage, higher amperage, the more you're going to see the output from the generator coils in the form of a pulse. And that's not, so the generator action is suppressed more because it's a lower RPM, and so the output of the generator coils is more of a capacitor system under load, far more. So normally if you're running this under load, depending on the type of load you're running, if it's really hard, this represents a medium load actually for this motor. You can still pull a lot more from the motor than what we're going to do here. 50-60 amps, we could go up 80 to 100 amps with these coils. And of course the MOSFETs can go way higher. Actually the MOSFETs allow for higher voltage, so we can go a lot higher voltage. We're going to be going into the hundreds of volts with these motors in the near future. So we should be able to do that even with these FETs without any modification to the motor. We just got to change the code a little bit and so forth. So with the newer coils we'll be doing that, and then this thing will probably be reach its physical limits as what it can do. But that's one reason why we upgraded the rotor to be a lot more powerful, and it's really well machined, so it works out really well. Anyway, all the beeps going on here. So what else is there to know? Yeah, we got the code where it starts up with this, and after so many pulses we turn on the second for the timing adjustment. And yeah, for the output of the generator coils now, if you read Tesla on impedance in that little paragraph that I point out so often and in my book, the pulsing from the EMP type of pulse here, we can benefit from that. This output then can do quite a bit more than what you would think. Like if you're trying to just close the loop, then you'll miss the point. So in this case the LED is indicating that, and we're just going to run it a little bit here because I don't want to blow it out. I'll probably damage it. The pulses will be really intense. So anyway, let's get our meters going again. And can turn out the lights. Of course, it's day here again. I should be fine with that meter there, except it's upside down. Alright, so we're going to turn out the lights here. Therefore, we're going to see, it'll be interesting to see how the LED it goes in sync with the blades. Doesn't look like the lights are out here because the camera adjusts. So you still hear that clink. If you don't hear that clink, then it's not right. So we're going to look at the amps. If you can't see them, I'll tell you. So we start off with the input battery 2545, because I was running it pretty hard for a while there. And then the charging battery 2430. Alright, so all I got to do is just give it a little push. You can see the input. As soon as I turn it on, LED lit up. So we've got 60 amps here. And the LED is pretty bright. I'll turn it up a little bit. About at its limits before I blow it up. Anyway, let's turn on the lights a bit. So we could turn off the LED. Of course, it doesn't make any difference, as you can see. Now, I don't have a lot of power in these batteries, so you can see the voltage drop is so the charging battery is 2770. The amperage is 54 amps, and the voltage input is 2240. There's a lot of airflow going on here. So you can see the LED is still on now because the generator action, and you can see the pitch of these blades is pretty steep here. Anyway, so I didn't really get a chance to look at the scope shot there. I suppose I can look at it again right here. This is kind of dangerous. So we have 170 volts peak to peak, 190. So anyway, so that's just one of the demonstrations that I like to do at the convention. And I will be doing 2 more conventions. I said in August, I think August 3rd and 4th, I'm just confirming it tomorrow, that we'll be doing in North Carolina, Charlotte, North Carolina. We'll do a meeting there, and then which will be a resonance meeting like the last one, and then we'll do 2 weeks later California in Lottie, California, which is LODI, which is near Sacramento and San Francisco Bay Area, about an hour from there in Central California. So both on the Friday and Saturdays coming up. So anyway, we can look at the voltages now. They're going to bounce back, of course, on this. We've got the input battery, see, is coming back to 25.8 and climbing back up. Charging battery under charge, going back down a little bit. And this is again relating to the fact that what we're doing is shuffling around the charges with this capacitor here. Now this one's a bit big. According to the spike there, at 190, we probably want to come down to 2 microfarads instead of the 2.2 here. And it's just what we chose to test this out. But again, we're going to be changing these coils to some smaller ones. Like I said, well, I have one right here. So we'll be using these coils. And we have bigger ones in here, but they were just a little bit too powerful. Under the first testing that we were doing. So we'll be doing those coils, which have some advantages with the core material, is a much better core material than these rods. And it allows for a lot easier pulsing, but there's a lot more of a pulse because of the coils. So we have to manage everything a lot more carefully. But anyway, like I was saying, the shuffling around of the energy, there's really now an operating of shuffling of charges that are circulating because of this. It's kind of like a series tank circuit in which you're shuttling around the energy, just like a resonant tank circuit, and you can see the oscillations across the MOSFET indicating that. So what happens is, as I said again and again, the spike shown across that cap is going to indicate how much charging takes place in this charging bank, as opposed to how much is circulating in the front end of the motor with the input battery. So this is moving more and more towards having the batteries just not discharge at all, neither charge or discharge, but the motor just runs. And again, in conjunction with doing what I call the third stage process, where the energy is flowing back into the input, and we have to again protect the MOSFET. So MOSFETs are running nice and cold. Of course, it stopped for a while here, but we are at 100 degrees right now, so they would probably run pretty hot. I do have water cooling. The more capacitance we add here, the more, the higher the peak pulse, and that's hard to understand. You can't really see it unless you have the right meters on this the scope probe and measure the peak pulse, the amperage. These are not going to show that. They're just going to attempt to show an average. So they're not really that accurate. True RMS, yeah, right. So anyway, what I'm getting at is the only thing you can see is the batteries over time. you can't just go by a 5-minute run like that, because you don't really get a feel for where it's doing that, so, or where it's going. So yeah, we're really satisfied with these motors now, with the code, and the changes we've made on the MOSFET. So again, this MOSFET isn't as good as the little one from the little kit, but that one has a low voltage capability, so it's very difficult to use that going above 12 volts. We can do 24 volts with the little motor, but trying to use this with this high inductance is not really possible. Like you can see, we're up there above, 190 volts on the spike there with those big capacitors across the FET. So it's probably best to stick with that, especially if we load this down a little bit more with these cap values, because the oscilloscope isn't showing you really the top end of the spike. It's only sampling it, and it's not going to catch that. So it's going to go way above the 500 volt rate, or limit of that. So we could do another test loading this down like I sometimes do with the pulley and the generator on it, but that would require a different setup. I thought I was initially going to do that with the big golf cart batteries. If we had the golf cart batteries, we'd be pulling higher amperage and we would be at a higher voltage because there would be such a big voltage drop. There's only at 22 something volts these batteries, because they can only put out so much without a big voltage drop. So if we were at 24, 25 volts with this fan, it'd be going a lot faster. We'd be pulling a little bit more amps and higher voltage. Now we can, as I said, if we ran this with the generator coil, a generator attached to the shaft, then we could pull this down even more. And we will be running this at 3648 volts. Essentially, if you're going to spend the money on something like this, you would really want to run this at 48 volts. And like I said, we're going to take it up to maybe a few hundred volts, at least over 100, and it'll be a different type of motor then, but it'll be the same parts. So anyway, if we run this the same amperage at a higher voltage, of course the power increases. I mean, you could see when we were running this at 12 volts, without really a load on it, it's not really worth it to spend the money on this, as opposed to the little motor. If you're going to run it at that low voltage, because you're going to have to get the amperage out of it at a low RPM. That's just the way it's going to work. So as we go up in voltage, we'll get a lot higher RPM on this with higher torque, of course. So that's it for now. And the next video along those lines will be changing of the coils, which will make it lighter for shipping, like 15 pounds lighter or more, and then it'll be thinner. So we could stack this up with the thinner one at least 5 times. I would say maybe like 7 times. Good 7 stacks, and then it would be a really powerful motor. I mean, this would be all you would need for a household. If you can do this 48 volts, 4,000 watts continuous, that's enough to you know, run your regular loads, which is, you know, like about 1.2 kilowatt average. So, you know, maybe 28 kilowatt hours a day. If you look at your electric bill, you can see the total monthly kilowatt hours divided by the month, and then you'll see your day. And that's your average. So if you're charging a battery up 4,000 watts continuous, you'd be way over that. And then also you could power your heat in the wintertime if you are in the cold areas, or air condition in the summer. See what these voltmeters kicked off. See what they're at. So you can see this battery is 25.21. That's the input battery. I think it was 25.4 or something when we started. Charging battery 24.43. Now again, the charging is as good as the size of the battery, so the bigger the battery bank, the more charging is taking place. This has been kind of bottlenecked. It's not going to be able to receive all the energy because the bank is very small. But the input, you can see, I mean, what kind of happens with these systems is they kind of balance out. If there's not enough battery on the back end, some of the charge ends, more of the charge ends up going into the input, back into the input. It's just going out, you know, and it's all every single part is connected, obviously, but is more connected than you think. It's very sensitive, all these things, so there's a balance. But the bigger the output, including the wire and everything, like we're not using the best wire here, it's just 10 gauge wire. Ideally you'd have big, thick, short wire right to the terminals, you know, and so forth, but it's good enough. So anyway, it's a system that works good as a motor or a generator or both, and it's something to definitely study. It's definitely fascinating to experiment with. So, well, thank you for watching. Once again, ending this video twice now, 3 times.